Welcome everyone to this video. My name is André Rode from the Karlsruhe Institute of Technology, and today I'm going to talk about the topic of optimization of geometric constellation shaping for Wiener phase noise channels with varying channel parameters. This presentation I've already held at the European Conference on Optical Communication 2022 in Basel, Switzerland. And the work on this topic I've performed jointly with Laurent Schmalen. So the motivation to work on this topic is to optimize the performance of high-rate coherent optical communication systems that employ the blind phase search as their phase recovery algorithm. And in order to do so, we apply geometric constellation shaping. And contrary to classical communications where the square QAM constellation is predominant and specifically well studied for the white noise channel, and also we know a lot about how to perform the bit labeling for these square gradual amplitude modulation formats, and also how they behave in various situations, especially in conjunction with a additive white noise channel. So in order to improve the performance on channels that not only have white noise but also have laser phase noise, and also employ digital signal processing algorithms like, for example, the blind phase search to recover the phase. There have been previous works on how to employ geometric constellation shaping, and also that it has a benefit on the performance in the end. And in one of these previous works, we already introduced a way how to perform the geometric constellation shaping for this channel that includes both white noise, phase noise, and also the blind phase search. And we got a constellation like this at the transmitter. So the transmit constellation here has, especially in the top right and also in the bottom left, it has points that stick out, that have an asymmetry, and from this result we basically propose that these points help this phase recovery algorithm to improve the performance. And in the previous work we have performed this simulation on a fixed set of channel parameters. So the next step is now to look into how this shaping and the performance changes if we also include the information about the channel parameters into the training of the neural networks that we use for this geometric constellation shaping. So in general, how do we perform this geometric constellation shaping? We use the bitwise autoencoder approach, and that means we want to transmit a vector of bits, here denoted as B1 to B small m. We send it through a transmit neural network encoder that in the end gives us the complex symbol xk. This complex symbol xk we transmit through a channel simulation, for example white noise or white noise and Wiener phase noise, or any other, in this case, should be differentiable autoencoder channel. We then receive an x hat k, also a complex symbol that is impaired by various channel impairments, and we send it through this receiver neural network decoder that in the end tries to approximate the log likelihood ratios for each of the sent bits. And in the end we transmit small m bits over the channel. The performance we measure with the bitwise mutual information that is shown here, and we can also use this either via the binary cross entropy as a loss function or directly use it as objective function. And the nice thing about this bitwise autoencoder is that it includes all of the bit labels in the training. So compared to, for example, a symbol-wise autoencoder, where we in the end obtain a constellation that is optimal or optimized for a set of channel parameters, we then in the next step, in a separate step, have to find a bit labeling which works on this given constellation. In this case, we already have the bit labels included and can use them further in implementation or further analysis. Yeah, so to include our system together with the bitwise autoencoder, we basically have in the middle this autoencoder channel where we have in NK, where we have in NK is the additive white noise. Here we add the Wiener phase noise process, which is described here with a parameter sigma phi squared. And here we then correct for the phase errors with the blind phase search. So either with our previously introduced differentiable blind phase search or with the regular blind phase search, which is non-differentiable. In the end, we also obtain this x hat k, which is the received complex symbol. Yes. In order to perform the analysis on the varying channel parameters, we have the transmit neural network has two inputs, the sigma n for the white noise, sigma phi for the Wiener phase noise, and we do the same in the receiver. So here the received neural network has 4 inputs essentially. So it takes the sigma n as a real number, it takes the sigma phi as a real number, and it takes the real and imaginary part of the received complex symbol to then give us this approximated log likelihood ratios here. And at the demapper, essentially, we for each constellation symbol, we perform this. We obtain a constellation parameterized with these channel parameters, and then essentially perform a selection function on which of the constellation symbols to transmit. And to optimize the constellation for all of the channel parameters, we select the sigma n and sigma phi uniformly within this given range of channel parameters. And we do this uniformly within the SNR in decibels and also linearly or uniformly within the line widths in kilohertz. And then in the end we obtain a mapper and a demapper that can process arbitrary input values for sigma n and sigma phi, but of course only within the value range they will make sense, and the performance is optimized in this range. So then let's look at the obtained constellation so we can reason about what that means. So first we also performed this shaping on an AWGN channel without additional impairments by the Wiener phase noise or by or correction with the blind phase search. So it's just the AWGN, and here we see essentially the effect for the change in SNR, where we here in blue show have a very low SNR, and in yellow we have a high SNR regime. And essentially what we can see is that for the blue we have points moving outwards, so increasing the distance to other points. So here these also move outwards from these points, and to then in the end have a normalized power, average power of 1, average energy of 1. Basically points in the middle will move together, and we did not include in this plot the bit labels, because then the whole plot will be even more unreadable. But essentially the points that move closer together, most of them only differ in 1 bit. So in the end if 2 points that only differ 1 bit fall together or cannot be distinguished at the receiver anymore, we lose essentially 1 bit of information. And I mean, some points still with this 1 bit will be separated, so it's less than a bit of information. And now we can also look at this parameterized constellation that has been trained with the Wiener phase noise channel and the blind phase search as phase recovery. So here basically we can see a behavior that essentially 3 points or 4 points at the outskirts for the low SNR case, they move outwards. And as for this, the results that we obtained for the channel that did not have these varying conditions, we basically also have these asymmetries that increase with decreasing SNR. So for worse channel, we have more asymmetries or stronger asymmetries that aid the blind phase search. Now, if we look at varying the laser line width, so we now fix the SNR to 1 value and change the laser line width. Basically what we can see is that most points don't move at all. So here we have a big region, or mostly all of the points in the middle, they don't change with change in laser line width, and only the same points that have moved a lot for the white noise, change in white noise, also move for the change in laser line width. In this plot, the yellow color is a high laser line width, so it's a worse channel condition, and the blue is a lower laser line width. So here for a worse channel, these points move a little bit outward, but they don't change a lot. It's a very small change. So now we can compare also the performance of these approaches. So first in the solid line we have the parameterized geometric constellation shaping. Then in the dotted line we showed a square or regular QAM case. But we also trained a neural demapper, so to have, let's say, a comparison to this case. And then we also have a robust channel which has been trained only on the residual phase noise after the blend phase search, or an approximated residual phase noise, I have to say. And then we can measure the performance in terms of the bitwise mutual information that can be transmitted for a given laser line width. And the color in this plot, so right now is only the 14 dB SNR is shown. So what we can see for the low SNR case is essentially that we have a quite huge performance gap, especially for the higher laser line width. The parameterized geometric constellation shaping provides a lot of performance gain to both the square QAM with the neural demapper and also to the robust case. The further we increase the SNR, so it's the system here with the robust case has been trained at a SNR of 17 dB. We see basically that this is the operation point, or the point where this constellation has been optimized to, and therefore the performance here is optimal or close to the parameterized geometric constellation shaping. If we then move to higher SNR, the performance gap again increases in favor of the parameterized geometric constellation shaping as we move further away from the point where this robust constellation has been optimized to. And we can also see for the higher SNR case that a square QAM for low laser line width also matches the performance with the parameterized geometric constellation shaping. So now to come to an end of this video, what are the conclusions of our work? So basically that we can analyze the results of the geometric constellation shaping also with the varying channel parameters, and that it's beneficial to obtain, let's say, a deeper look into how the geometric constellation shaping performs for different channel parameters. Then we also see that the adaptation, that we can adapt the transmit constellation to the and the demapper to the different channel parameters, and this offers an advantage over robust constellations and just using regular square QAM. And in the end, we also saw that for the laser line, change in laser line with a small change can have quite significant impact on the performance of the constellation. I want to thank you for the attention, and if you have any questions, feel free to email me or put your question in the comments down below.